Globally, thousands of industrial accidents are linked to process safety incidents, accounting for a disproportionate number of fatalities and economic losses, claiming thousands of lives and causing billions of dollars in damage annually. Because of these severe consequences, industries such as oil and gas, power generation, and chemical processing rely on dedicated protection layers beyond basic control systems, one of the most critical being Safety Instrumented System or SIS. An SIS is an independent system designed to detect hazardous conditions such as overpressure or abnormal process states and automatically place the process in a safe condition before escalation occurs. In this project, I model and simulate a safety instrumented system for a fuel gas supply inlet using MATLAB and Simulink. The model reflects how an actual SIS operates in industry, from process conditions through sensing, safety logic, and finally shutdown action. This approach validates SIS performance under normal and fault conditions before real-world deployment. I will now walk you through the safety instrumented system model developed in Simulink. On the left side of the model, I have represented the fuel gas inlet process. This subsystem models the flow behavior of the gas in the pipeline, including both inlet and outlet flow conditions. Here, process pressure is calculated using real gas equations together with the Darcy-Weisbach equation to account for pressure drop along the pipeline. I modeled gas temperature using the Joule-Thomson effect and specific heat capacity to represent the heater dynamics. Together, these subsystems allow the physical process behavior to be simulated under normal operation as well as under abnormal conditions. This set of subsystems represents the flow, pressure, and temperature sensors respectively. Each sensor is modeled using transfer functions based on the response time and time constants obtained from product datasheets. The sensors continuously monitor the process variables and their signals are fed into the safety logic just as they would be in a real SIS, independent of the basic process control systems. Here, I used a MATLAB function block to represent the SIS logic solver. Safe operating limits have been defined based on the case study, and whenever a process variable exceeds these limits, the logic evaluates whether a trip condition has occurred. In this model, a voting logic is implemented using 1 out of 2 voting for flow sensing and 2 out of 3 voting for pressure and temperature sensing. This reduces spurious trips while maintaining safety integrity. Once a trip condition is confirmed, the SIS sends a command to the final elements, including the emergency shutdown valve and control valves. This action isolates the fuel gas supply and brings the system to a safe state. The state of the valves can be seen on the HMI, the human machine interface, by 0 meaning it's closed and 1 meaning it's open. On the HMI, you can also monitor real-time parameters such as pressure, temperature, and flow rate. The callback button observed here is used to set the flow inlet, and the toggle switch there is used to reset the emergency shutdown valve in cases of trips. As shown in the plots here, under normal operating conditions, the SIS remains passive while continuously monitoring the process. But in this case, when an overpressure condition is introduced, whereby the pressure rises beyond the defined safe limit, it is observed that the SIS logic activates, closing the shutdown valve and opening the pressure control valves to prevent further escalation and relieve the pressure within the pipeline. These are plots observed for flow and temperature anomalies as well. These plots compare the system response before and after the SIS action, clearly showing how the process transitions from a hazardous condition to a safe state. This type of modeling allows safety behavior to be validated early in the design phase, reducing risk and improving confidence before deployment in a real-world environment. My name is Olochukwu Osakwe, and this is my entry for the Simulink Students Challenge. Thank you.